So in this video, we're going to work on working through some matrix multiplication and then finding inverses and determinants of some matrices. We're going to mostly worry about 2 by 2s for inverses, but we'll also talk about how we can do it with any square matrix. The first thing we want to talk about is matrix multiplication. So when we're doing matrix multiplication, what we need to know is that order matters. This is really important. Order matters. That means taking two matrices and multiplying them together with like matrix A times matrix B first is not going to be the same as what happens when we multiply them in the opposite order. Matrix B times matrix A is not equivalent to matrix A times matrix B. So the way we multiply two matrices together is first to be able to determine if we have to determine if it's possible to multiply two matrices together. Not all matrices can be multiplied by each other. And to get to that, we need to look at the number of columns in matrix A, and it must equal the number of rows in matrix B. So we can look at the dimensions. So for example, if I have this row by column matrix, it's a 3 by 2 matrix is matrix A, and then matrix B row by columns is 2 by 4. Then what I need to look at is, do the columns in A and the rows in B match? And if they do, then I can multiply A times B in that order. Okay, so to do that, one of the things I like to talk about is that you look at the inner dimensions. These two dimensions, the ones here, are they the same? And if they are, then the dimensions of what will happen when I multiply them together are the outer dimensions. So the matrix AB is a 3 by 4 matrix because of what's left on the outside. Okay, now just as a kind of to check things out, could I multiply B times A? That's think about that. So B, remember, is 2 by 4. A is 3 by 2. And this time, those two dimensions do not match. And this is not a match. And in that case, I cannot do this. This is not possible. All right. So order does in fact matter here. All right. Let's move forward. Let's look at a little example of some multiplication. So I took a 2 by 2 matrix here, and I'm going to try to multiply it by a 2 by 3 matrix. And this is just showing you the process. So I'm going to kind of step through it a little bit at a time. So to do this, now that I know that I can multiply them, their inner dimensions do in fact match. So it's going to end up with a 2 by 3 matrix, right? I start off with the very first row in the first matrix, and I'm going to multiply it by the very first column in the second matrix. And what I get from that is this. The first number here gets multiplied by the first number there, 3 times negative 2. And then the second number in the first matrix gets multiplied by the second number in the second matrix, so negative 1 times 3. And we continue on in this fashion. Now I'm going to take the first row and multiply by the second column. So 3 times 0 and negative 1 times 5. That's where I get these answers. Then I'm going to take that first row and multiply by the third column. So the 3 by the 6 and the negative 1 by the negative 1. That's how I get this entry. Now I've done the first row by every single column in the second matrix. So now I'm going to go down to the second row and multiply it by each column. 4 will get multiplied by negative 2, 0 by 3. 4 times 0, 0 times 5. And 4 times 6 and 0 times 1. And we'll add those individual rows and columns up. Okay, so once we've done that, we would, simplify those answers, and it'll give us the final answer. So notice to find the element in the first row, first column, we take the first row of the first matrix and multiply by the first column of the second matrix. To find the element in the second row, third column, we take the second row of the first matrix and multiply by the third column of the second matrix. So this is just kind of giving you a pre-written example of how to multiply. Alright, so I want to see if I can, if it's possible, I want to find the product. So this has 3 rows and 2 columns, and this one right here has 2 rows and 3 columns. So is it possible to multiply A times B? Yes, it is. Their inner dimensions do in fact match. And the resultant matrix I will get is going to be a 3 by 3 matrix. So I'm going to come now and I'm going to try to multiply them out and see what I get. So we'll have 4, 5 times 7, 2. 4 times 7 is 28. 5 times 2 is 10. That goes in the first row, first column. Now I'll take first row by second column. 4 times 0 is 0. 5 times 6 is 30. Then I take the first row by the third column. 4 times 1 is 4. 5 times 8 is 40. So already, just by simplifying this, I'd have 38, 30, and 44. Now I've done the first row. I need to come in and do the second row. So now 19 by 7, 2 is going to be 7 plus 18. 9 times 0, 6 is going to be 0 plus 54. And 9 times 1, 8 is going to be 1 plus 72. So I end up with 25, 54, and 73. Last, I have the third row. Negative 6 times 3 is going to get multiplied by 7, 2. So negative 6 times 7 is negative 42 plus 6. Third row by second column, 0 plus 18. Third row, third column, negative 6 plus 24. This gives me negative 36, 18, and I think 18 again. Alright, so that is what happens when I multiply matrix A times matrix B. Now the question is, can I multiply B times A? Remember, B is a 2 by 3, A was a 3 by 2, and again, their inner dimensions match, so I am able to multiply these two matrices together. So again, I'm going to I'm going to do it in the opposite way. So we're going to erase, we're going to erase up our little rows and columns here. We're going to do it in the other way. This time I'm taking the rows in B and multiplying by the columns in A. So 7 times 4, 28, 0 times 1, and 1 times negative 6. Now I want to take that first row and multiply by the second column in A. 7 times 5, 35, 0, and 3. Now we're going to go down to the second row and multiply it by all the columns in A. 2 times 4 is 8. 6 times 1 is 6. And 8 times negative 6 is negative 48. Now I'm going to multiply by the second row, the second column. 2 times 5 is 10. 9 times 6 is 54. And 8 times 3 is 24. We'll add these things all up. We get 22, 38, let's see, 14 minus 48 is negative 34, and then I get 88. Okay, so that gives you two good examples of multiplying some matrices. Now let's talk about identity matrices. So what is a identity matrix? So to talk about what an identity matrix is, we need to make sure we remember what an identity is in the real numbers. The reason something was a multiplicative identity in the real numbers is because the reason the number 1 is our multiplicative identity is because a times 1 is a. So basically, it's when I multiply it by something, I get back the exact same thing I started with. So the multiplicative identity for matrices is a square matrix, okay, with 1s along the main diagonal. So 1s along the diagonal here, and 0s everywhere else. So if I have this is called an identity matrix. So basically I2 is a 2 by 2 identity matrix, 1 0 0 1. I4 would be 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. Okay, so basically I can by I and then whatever subscript I have down here talk about different sized identity matrices. All right, now let's talk about what an inverse of a square matrix is, how to find one of those, what it is, and how to find it. So again, in the real numbers, let's talk about our real number equivalent. The multiplicative inverse of a number a was 1 over a, because when we multiplied a by 1 over a, we ended up with the identity. So a times 1 over a is 1. The multiplicative inverse of a square matrix is called its inverse matrix. That means that if I take the matrix multiplied by its inverse, I get the identity matrix. So that's how I can tell that two things are identities, or excuse me, are inverses. And the way we write an inverse in matrices is with the -1 subscript, which I think we've talked about when we were in trig. My issues with that subscript, how I don't really particularly care for it because it's a little bit ambiguous in some cases. Okay, so let's talk about whether or not these two matrices are in fact inverses of each other. Well, the way I know to check that is to multiply them together and see if I get the identity matrix. So I'm going to multiply a times b. So I'm going to take -3, 2, -2, 1, and I'm going to multiply it by 1, -2, 2, -3, and I'm going to see if I end up with the identity matrix. And if I do, then these two things are inverses, and if I don't, then they're not. So -3 times 2, or 2 times 1, 2, is -3 plus 4. -3, 2 times -2, -3 is 6, -6. Multiplying into the second row now, -2 times 1 is -2, 1 times 2 is +2, and -2 times -2 is +4, and 1 times -3 is -3. When I simplify this, I end up with 1, 0, 0, 1, which is in fact the identity. So yes, A and B are inverses. Okay, so let's move on. Another way you can find an inverse of a matrix, maybe or one way to find an inverse is, let's say I wasn't given the other matrix, right? They actually want me to find out what the inverse is I can do this thing that's called creating a doubly augmented matrix. So we've talked about what an augmented matrix was. I did that in the last video. So in this one, a doubly augmented matrix means I take my matrix and I augment it with the identity matrix of that size. So for example, 8, -5, -3, 2, I'm going to put that with 1, 0, 0, 1. And what we do is we're going to take this particular matrix and we're going to put it into reduced row echelon form, which will basically move the identity matrix to the other side. And when we do that, what's left on the right will be my inverse. So what I'm trying to get to is a 1 here with a 0 underneath, a 0 here with a 1 underneath. That's what I'd like. Okay, so to get the 1 in the first spot, I'm going to kind of do some tricks to try to keep this thing from turning into fractions early. So I know that 8 and 9 are pretty close. I also know that 16 and 15, I'm thinking about multiples of these things, are 1 apart. So if I take 2 row 1s and I add it to 5 row 3s and or row 2s, excuse me, and put that into row 1, I should end up with a 1. So let's see, that is 16, -10, 2, 0, and 5 of these is -15, 10, 0, 1. When I add that, I get 1, 0, 2, 1. So right now what I have is 1, 0, 2, 1. Now, that actually worked out really nicely. I want to now get the 3 to be a 0. So I'm going to take 3 row 1s, and I'm going to add it to row 2, and I'm going to put it in row 2 spot. That means I'm going to be taking 3, 0, 6, 3, and adding it to -3, 2, 0, 1. When I do that, I get 0, 2, 6, 4. So my matrix has now become 1, 0, 2, 1, and 0, 2, 6, 4. Okay, so now to finish this up, I'm going to try to get that first term to be a 1. To do that, I'm going to take row 2 and I'm going to half it. When I do that, that gives me 1, 0, 2, 1, 0, 1, 3, 2. So I get that a inverse of this particular matrix, assuming I did my math correctly, which now I'm starting to doubt for some reason, is 2, 1, 3, 2. Yeah, it just feels incorrect here, so might have made a little mistake somewhere in yeah, I must have made a mistake. I may come back to this one. Oh, I know. No. Yeah, I know what I did. This should have been a 5. And so that should have been a 5. So this should have been 2, 5. And then when I came in here, I took 3 row 1s. That 5 would have been a 15. So this would have been a 16. And so then when I halved everything, that would be an 8. And this was a 5 the whole time. So the final answer should be 2, 5, 3, 8. Okay, good. All right. Hope that made some sense. If not, let me know, and I'll be happy to walk through it again. All right, I want to find the determinant of a 2 by 2 matrix. It's very simple. We multiply diagonal down, so I get AD. Multiply diagonal up, I get BC, and then I take the bottom minus the top. That is what is called a determinant of a matrix, okay? Don't worry too much about this. They are used in a lot of applications. For now, just kind of think of it as assigning a value to the matrix, okay? So to find the determinant of this matrix, I'm going to multiply down, that gives me 8, multiply up, that gives me -12. I do 8 minus -12, and that gives me 20 is the value of the determinant. Multiply down, that gives me 40, multiply up, that gives me 40. 40 minus 40 is 0. The determinant is 0. What's one application of this? Well, I can use the determinant to be able to help me find the inverse of a matrix a little bit easier than that doubly augmented method. To do that, you do have to memorize a little bit. You have to know that the inverse is what happens when you swap these two and you change the signs of the other ones, and then you multiply by the reciprocal of the determinant. Okay, you can only find an inverse of a matrix if the determinant is non-zero. Okay, so let's look at this one. Let's see if, first of all, if it's possible to find the determinant. So, or if it's possible to find the inverse. So this is 8, this is negative 12. 8 minus negative 12 is 20. So the inverse is 1 over 20, 1 over the determinant. Swap the ones in the main diagonal. Change the signs of the others. So if I wanted to multiply that all the way through, that'd give me 4/20ths, or 1/5, 3/20ths, negative 4/20ths, negative 1/5, and 2/20ths, or 1/10. Or what about this one? Multiply up, that gives me 40. Multiply down, that gives me 40. 40 minus 40 is 0. This and is not possible. This particular inverse doesn't have, or this particular matrix does not have an inverse. All right, how can I find the determinant of a 3 by 3 matrix? Well, there are two common methods to find that. One of them is called an expansion by minors, and one of them is the column method, or the lattice method. I'm going to work some examples both ways. This is the column or lattice method. What we do is we rewrite the first two columns, we multiply the diagonals, we add the products from each direction, and we subtract the bottom sum from the top sum. So here's an example: 3, 2, 1, negative 4, 1, 6, 0, 5, 2. Okay, so there's my 3 by 3 matrix. So the column lattice method says first, rewrite the first two columns. What they mean is at the end. So I write 3, negative 4, 0, 2, 1, 5 going down. Then what we want to do is we want to find the diagonals that go up. So here is one of them. Here is another one. And here is a third. And then there's some columns that go down. Here is 1, here is 2, and here is a third. Once I've found those columns going up and down, I multiply the numbers in each of those diagonals. So this is 6, the next one is 0, and the next one is negative 20. When I add all those up, I get negative 14. I'll do the columns going up. That gives me 0 plus 30 times 3 is 90, plus negative 16, and that is 74. Then I do the bottom, negative 14 sum, minus the top sum, minus 74. That's a negative 88. So that's how you find the determinant using the column or lattice method. Very simple, very straightforward. Just the hardest part is keeping your diagonals straight, remembering to add them all up, and remembering to do bottom minus top. Okay. Here's expansion by minors method. You can use this with larger matrices, even ones larger than a 3 by 3. But again, let's go 2, 0, 5, negative 4. Let's not do 0. That's going to be confusing. 2, negative 3, 4, and let's do negative 4. 5, 6, negative 1, 2, 4, 3. So here's the deal. When you're doing the expansion by minors method, what you have to remember is to assign every location in a matrix by a particular positive or negative value. So for a 3 by 3 matrix, any matrix, it always starts with a positive in the top left corner, and then we basically alternate signs. Okay. So this method that we did right here, this like assigning of these values, is going to help me when I'm doing my expansion. And I'm expanding it by finding out smaller matrices. These are my minors. And the process that we're going to use is we're going to basically pick a column to be my anchor column. Okay, a row to be my anchor row. My anchor row, typically for me, is the top row. Okay, I choose that frankly because it's the easiest for my brain. All right. whatever the sign is attached to that goes out in front. So, for example, when I'm making my expansion using my 2, it's in the positive spot, so I'm going to do plus whatever this number is. It's a 2. If it had been a -5, it'd be plus the -5, okay? So then I'm going to make a little matrix here. Then I'm going to do one with the next spot. My next spot is my -3. Okay, I have a minus here, so I'm going to do minus my -3, which is going to make a +3. And then lastly, okay, so this is, I probably shouldn't have put the brackets like this because technically when we're doing determinants, we normally use these kind of parallel lines, but that's fine. And then a plus for the last one because it's in the plus spot, a -4. And again, I guess just for consistency's sake, I'll leave them in the same type of brackets. So this is part of my expansion. How do I find out the rest of it? Well, the way we do the rest of it is we take our, if I'm doing the 2 matrix, I cover up the 2, okay, and the rest of that column, the column is gone, and whatever is, so I guess I can make myself a little, undo that, a little rectangle to go the other direction so you can kind of see it a little bit better. Alright, and let's fill it in purple like the other one. So we're going to put this here. Alright. And what's left in there is the matrix that I fill into my spot. So in this case, that is 6, -1, 4, 3. How do I find out what goes in the 3 matrix? Well, in the 3 matrix, I'm covering up my -3 column, and I'm putting in I'm covering up the row that was my anchor row, and I'm putting in what's left. In this case, that is 5, -1, 2, 3. And then lastly, to do the one with the -4, I cover up the -4 column and row, and I'm left with 5, 6, 2, 4. Now, to finalize this, what we do is we find the determinant of each of these 2x2 matrices, multiply them by the number that's out in front, and then sum all of this up. So I have 2 times, multiply down is 18, multiply up is -4, subtract the -4, plus 3 times, multiply down, get 15, multiply up, get -2. So I have 15 minus -2, minus 4, multiply down, get 20, multiply up, get 12. So I have 4 times 20 minus 12. That's 22 times 2, 44, plus 17 times 3, 51, minus 4 times 8, which is 32. So 63, I think, is the determinant of that 3x3 matrix that I started off with. Alright, so this is the expansion by minors method. And by the way, it works for any sized matrix. Okay, if we were a larger matrix than this, if we were a 4x4 or something, then we would have more work to do. Our first expansion by minors would drop us down to 3x3s. Then we'd have to do another expansion of minor on the 3x3s to drop us down to 2x2s. Alright, so let's see if we can find the determinant and then find its inverse if it exists. So I'm going to do one of these by the column or lattice method and one of these by the expansion by minors method. I'm going to do the top one by the column or lattice method and the bottom one by the expansion by minors. So repeat my first 2 things. Okay, 2, -1, 4. Multiply down, I get 3, or 0, excuse me. Multiply down, I get -4. Multiply down, I get +16. Multiply up, I get +4. Multiply up, I get -24. Multiply up, I get 0. I end up with 14 and -20. So my determinant is 14 minus -20, which is 34. Expanded by minors method, I'm going to have 3 times its matrix, which is 2, -1, -1, 3, when you cover up that row and that column, minus 1, cover up that row and that column, get left with 1, -1, 2, 3, and plus 2, cover up its row and column and get 1, 2, 2, -1. Multiply down, get 6, multiply up, get 1, so I have 3 times 6 minus 1, minus 1 times, multiply down, get 3, multiply up, get -2, 3 minus -2, and multiply down, get -1, multiply up, get 4, so I have 2 times -1 minus 4. So I end up with 15 minus 5 minus 10, which I get 0. Alright guys, so that's the last bit you need to know for this little section. I hope this was useful. Again, if you have problems, questions, concerns, leave a comment or send me a message. See you guys around.